Have you ever wondered how your game manages to handle movement between you and 60 players, sometimes worldwide? No? You just get mad at the lag and move on? Well, me too. But I sat down and really thought about it. How can a game like Apex or Fortnite handle 60 plus players moving in unison all at once? Oftentimes with little lag. How in the world does any of this work? And how have I never sat down and thought about this before? So I sat down, did some research, and I'm hoping I can explain simply what I've learned. To understand how a server actually syncs 60 players moving in unison, we're going to build a game server in Python and cover 5 key engineering concepts. First, why traditional HTTP fails for games, and how persistent WebSockets enables real-time two-way communication. Second, how a 60 Hz tick loop and Python's Asyncio keep us under a strict 16.6 millisecond frame budget. Third, how a spatial grid positioning solves the O(n) squared network bottleneck when dozens of players move in the same area. Fourth, how we package everything into Docker so it deploys seamlessly to any cloud server. And finally, we'll run a live benchmark spawning 60 simulated player bots moving simultaneously to watch our server handle the load live on screen. Let's dive in. So, if you tried to build a multiplayer game using standard HTTP requests, your game would literally be unplayable. Think about how an HTTP request actually works. Every time you send a request, your computer opens a new TCP connection, packs on a bunch of heavy headers, waits for the server to reply, and then tears the connection down. Imagine pressing W to step forward in Apex, but before your character takes a single step, your game has to dial up the server, hand over a formal envelope saying, "Dear server, please move me 1 inch." Wait for an approval, hang up. By the time your character actually moves, the match is completely over and you've died to the zone. It's way too slow for real-time action. So what do games actually do? Well, instead of opening and closing connections over and over, games use WebSockets. Think of a WebSocket like opening a persistent two-way phone line between your game and the server. You make one initial connection when you launch into the match, and that line stays open the entire time. Now both your laptop and the server can stream raw movement data back and forth instantly with zero lag or header. So what actually is a tick? Think of a tick like a heartbeat of a game server. On every single tick, the server runs one complete loop. It reads incoming player inputs, updates world positions, resolves collisions, and broadcasts the new state back to all 60 screens. At 60 ticks per second, the server has a maximum budget of 16.6 milliseconds to finish that entire loop. And at 120 Hz, that shrinks to just 8.3 milliseconds. If a tick overruns its budget, the game hitches and rubber bands. Now to be clear, AAA games like Apex or Fortnite don't run their backends on Python. They're built in C++ for maximum speed, but Python's Asyncio uses the same non-blocking event loop architecture, allowing us to build and understand a real 60 Hz server in a clean, readable code. So how does Python actually handle 60 connected players at the exact same time without crashing your CPU? In traditional programming, you'd have to spawn 60 heavy OS threads, which chokes your system. Instead, we use Python's Asyncio. When the server is waiting for network data from one player, it doesn't block the CPU. It yields control asynchronously to process the next player. This non-blocking event loop lets a single CPU core manage thousands of open player sockets effortlessly. When 60 players drop into a battle royale map and start moving simultaneously, broadcasting every single player's position to everyone else requires 3,600 network messages every single tick. At 1,000 players, that explodes into 1 million network packets per tick. This big O of N network bottleneck is why unoptimized multiplayer servers lag when everyone moves at once.
The solution turned out to be surprisingly simple: spatial grid partitioning. I mean, just think about it. If you're sitting on the top left corner on the map, why on earth would your computer need to process movement on someone on the bottom right of the map? You literally can't even see them. So instead of broadcasting data to all 60 players, we chop up the map into a 2D grid. Players only receive updates from entities in their own grid cell or the ones right next to them. And just like that, we cut down our network traffic from an exponential nightmare to a smooth linear scale. Building a great game server is only half the battle, though. Deploying it is the other. I mean, just think about it. Look at all the different devices out there: PC, Xbox, PlayStation, cloud servers, custom Linux rigs. And think about all the different tech stacks out there, whether a server is built in C++, Rust, C Sharp, Go, Python, or literally any other language out there. Every single machine is running on different operating systems, different runtime environments, and different system libraries. So if you try to ship your server right now, it's going to crash on half of your players' machines just because their environment is missing one tiny dependency. And that's without even taking into account all the different software versions out there. And that's where Docker comes in. Docker solves the classic "it works on my machine" nightmare. It works by taking your entire game server, your code, your runtime, compiled binaries, and every single dependency, and locking it inside a self-contained, standardized container. Once it's containerized, whether it's written in Python, C++, or any other language, if it runs on your laptop, it's guaranteed to run anywhere on Earth. We write a simple Docker file starting from a lightweight Python 3.11 base image, setting the working directory, installing WebSockets, and exposing port 8000, all with one command: Docker run. Our game server spins up in seconds inside an isolated container, ready to be deployed anywhere worldwide. Okay, so now with this Docker set up, let's put our architecture to the test. We launch our Dockerized Python server and spawn 60 simulated player bots, pushing real-time movement vectors over WebSockets. Look at the dashboard: 60 players moving simultaneously. Spatial grid updates firing, and the server holding a steady 16.6 millisecond tick rate with 0 dropped frames. You've now built a real-time multiplayer game server in Python and containerized it with Docker. You can grab the full source code on GitHub, linked down below. If you want to see more real-world software engineering projects like this, hit subscribe, and I'll see you in the next video.